In this video, we are going to talk about marginal analysis for businesses. So, when we talk about equations that are relevant to businesses, we have a price demand equation. Usually, this is a linear function, and we'll use a lowercase p to represent that equation. That tells you the price that you would sell each item for demand X. And then we could come up with a cost equation. That would be the cost of running the business for selling X items. And that's going to usually include things like if you're renting a property or electricity, how much it costs to run all of the equipment in the facility. Um, in real life, you would also include things like what you're paying employees, etc. And then we're going to have revenue and we're going to have profit equations. So revenue is how much money you bring in. So the revenue equation would be the number of items you sell times the price for each item. So for revenue, the number of items we sell, we could show by X, and the price is going to be dictated by that price demand equation. So it's going to be X times P of X, or we could just say X times P. And then profit is how much you have after you've accounted for cost, which we would call C of X. So profit, I'm going to use capital P here, is going to be revenue minus cost, which would be R of X minus C of X. Anytime we hear the word marginal cost, marginal revenue, or marginal profit, we're talking about rate of change. So we're going to talk about the derivative here. So let's look at how we would find marginal revenue in this example. So we have a price demand equation. So it's 9 minus 0.03x, and this equation is good when x is between 0 and 300. They found the marginal revenue for us, which was very nice. They didn't have to do that. It's x times p of x. It's the number of items we sell times the price. So the number of items we sell would be x. The price would be 9 minus 0.03x. So we're going to end up with this quadratic when we distribute that x. And that revenue equation is going to be good for that same domain here. We want to use the marginal revenue function to estimate the revenue attained from selling the 101st barbecue dinner. So we first got to find the marginal revenue equation. So to do that, we're going to take the derivative. So it's going to be negative 0.03, bring the exponent down, subtract 1 from the exponent. Same thing for the 9x. That's an understood 1 as the exponent, so I'm going to bring the exponent down, subtract 1 from the exponent. So negative 0.06 plus 9 is my marginal revenue equation. So now we want to estimate what's happening with the 101st barbecue dinner. This is where it's going to get a little tricky. We're going to actually plug in 100 here, and I'll explain why in just a minute. And I'm multiplying this off screen, and then I ended up with 3. So what this is saying is that the marginal revenue for producing that next barbecue dinner would be about $3. Now let's find that exact value and compare. So to find the exact value, we're going to take and produce 101 items, and we're going to subtract producing 100 items. And notice we're plugging this into the revenue equation, which is this guy up here. So I have negative 0.03 times 101 squared plus 9 times 101. And then we're going to subtract. So this would be the revenue for producing 101 dinners. This is going to be the revenue for producing 100 dinners. And if I subtract it, I'll get the revenue for producing just the 101st dinner. I'm going to plug this in my calculator off screen. And when I do that, I get $2.97. So this would be the exact change in that revenue where this is approximating. So let's look at why. Why did I plug in the 101 and why did this work? It goes back to that limit definition. So when we talk about revenue, the marginal revenue would be the limit as h goes to 0 of r of x plus h minus r of x divided by h. So if I'm talking about selling items, the smallest I could ever be here is 1. And what's going to happen is when we look at that revenue, in case I'm looking at what happens when I sell the next item, it's going to be approximately equal to the limit as h goes to 0 of r of x plus 1 minus r of x. But remember, the smallest this could ever be is 1. So this is going to be approximately equal to because I can't get any smaller than 1 when I'm selling items. I can't sell a fraction of an item. I have to sell a whole item. So we're really looking what happens as we get close to 1 here. And you can see how that marginal revenue at 100, if I were to plug 100 in here, would approximate what's going on. So we can use that same theory to look at this one. We have a profit function here. It's the profit from selling X number of fish fry dinners. We want to find the marginal profit function to estimate the profit from selling the 101st. So we need to find the marginal profit equation. I'm going to bring the exponent down and subtract 1 from the exponent. I'm going to go ahead and just do that. So there's my marginal profit equation. I want to know what's happening on the 101st. So I'm going to plug in 100 here, and that would give me that approximation. And I got 2. So we would expect to profit about $2 on that 101st dinner item. So remember, this is an approximation. So to find the exact, just so we could compare, we would find P of 101 and subtract P of 100. This would be the profit for all 101 dinners. This would be the profit of just the 100th dinner. And we're plugging that into this equation. So I'm going to use some brackets here. Oops. So there's the profit of the first 101 dinners. And we're going to subtract the profit of producing 100 dinners. And then when I plug this in, I did this off screen again. I got $1.97, and this value should always be really close to this value because that's the whole point of this. This is actually finding something called a differential. Differentials are used to approximate exact values. Now, in these cases, these are really simple equations. We're dealing with quadratics. In both examples, a quadratic's really easy to find the exact value for, but in real life, you're going to have a lot more variables, and you may not be dealing with a quadratic function. You may be dealing with something that's not as nice, so it may not be as easy to find that exact value, and that's where the differential really shines, where you need to approximate, but you don't have a good way to do it because the equations are too complicated.